Hi, uh, Prakash here. This is the session 4, part 2, and we will re-record with Google later, but at this time I'm going to just present on his behalf. He has prepared the slides. So what we have here is continuation of what I had done session 4, 1 part 1. This is session 4, part 2. So I'll recap first what we did and then go ahead with the operator rule, bracket notation, eigenvalue, and Hermitian matrix, Copenhagen interpretation, Bond's rule, and projection operators and the problems. It starts with operator rules. So if you have a matrix M and it rotates a vector, say uh, k alpha, and results say in a vector which is uh, prime, alpha prime kit vector. So this is denoted as kit alpha prime equal to matrix M into kit alpha, and the operation happens as M multiplied by kit alpha. So kit alpha is the vector. So if there are two operators M and N, so this is the linear combination. Like A into this is like you have a vector and you are multiplying by matrix. It is like M by alpha, kit alpha. So this is vector and the new vector is vector. So generally when you operate a matrix on a vector in the what do you call the Hermitian space, you are getting a new vector. And if you have two matrices, then what happens? And that means uh, if you have two matrices and they operate on the same vector and yield the same output, then M and N must be same. So what it means is if M ket alpha is equal to N ket alpha, and for all ket alpha, N is equal to N. So this is also true for null vectors. Of course, when you say 0, 0, and then you are putting a ket 0, that means what is applicable true for 0, 0 vector? Uh, that's M and N can be 0, 0 also. And plus the bra vector, what is applicable for uh, ket alpha can be also be applicable for bra alpha. That means what? Uh, Whether you use a ket notation or bra notation, but the multiplication of one vector to another vector for the same vector will be resulting, if they are same, then the matrix themselves are similar. That's what it is. Now, zero operator. Obviously, we saw null is defined 0, 0. So uh, here a 2 by 2 matrix with a 0 is considered as null. You can have n by n. The operation represented by anything multiplied by 0 is 0. So in this case, ket 0 or operator, null operator multiplied by ket alpha is ket 0. So basically, this is very similar to our basic primary mathematics. 0 multiplied anything 0. So in this case, 0 matrix multiplied by any vector is 0 matrix or 0 vector. That's what it is, which is null vector. Distribution law. This is one of the property of operator M. So matrices we generally represent, we call here in our term quantum as operator. So operator M should exhibit distributive law. That means what? If M, if we have uh, complex alpha and complex beta, it's two coefficients of kit alpha, the two bases, let's say kit alpha and kit beta, then M matrix M multiplied by C alpha ket alpha C beta plus C beta K beta equal to we are multiplying taking the C alpha, which is a complex number, multiplied by n, and same way complex beta number multiplied by n, and so C alpha C beta are scalar any complex number. So essentially what it means is these are distribution law, that is A into B plus C is equal to AB plus AB types, which is we do in algebra very similar like that. In this case we are operating with matrix, but the order will keep the same in the sense that we can move any scalar to the left rights, but we don't move any vectors to the right left. Vectors remain where they are. If they move, then kit will become bra, so that's avoidable. That's not do. Then, so applying a matrix M, which is operator, it rotates on a linear combination of two vectors in the same as rotating them individually and performing linear combination of the two vectors. So essentially, that's what we saw earlier also, that uh, you apply one and then the other. It depends upon uh, if, if it is with respect to a linear combination, obviously this is different from what we saw there. There we saw two consecutive application of matrices, M1, M2 followed by vector. So we say that you have to apply M2 first, then M1 later. But here there is only a single matrix and the rest is scalar. So this is distributed. It will apply distribution law will apply A to A into A into B plus C equal to AB plus C types. That is applicable here. M into ket alpha, and that is C alpha, ket alpha, C beta, beta, uh, ket beta. That is equal to C alpha M ket alpha, C beta M ket beta. Next. So operators can be in ket and bra space, as I explained earlier also. So if you have alpha ket, then corresponding bra space is bra alpha. So this is ket alpha, bra alpha with a greater sign here and less sign early. And that's a vector sign. So we can rotate. If we have rotation, we get a in the ket space when we rotate. What we get a new vector alpha prime. Same way, if we had done the same thing, we can represent them in bra space, but with a complex conjugation. Basically, that means because this is imaginary, real imaginary, let's say, and if we see real space and ket alpha equal to new alpha prime, and so the matrix multiplying the vector gives you a new vector. Same way, we can get a new vector, but you know that vector cannot be moved arbitrarily. So if it is a vector, it has to go as a complex conjugate. Same way. So in the bra space, everything is complex conjugate. So you have M becomes M dagger, alpha, which is a vector, ket vector, that becomes a bra vector. And if it's a bra vector takes the precedence over the matrix. So M of ket alpha is equivalent to bra alpha M dagger. So the corresponding vectors are maintained, but they have to be in a space because it is in the adjoint space. The adjoint operator applies here, and that's how we do. So the matrix which we saw adjoint of a matrix, that is what is applied here, so that you know that they are in a similar space. At the same time, they happen to be producing the same result. So we have seen distribution law. What is applicable for ket is also applicable for bra. So what it means is when we do uh, a complex conjugate of distribution law applies, and so whatever we did in ket space, we can apply it to bra space, and they will always be, of course, be complex conjugate, and accordingly it's applicable. We have seen the previous one. I just go back. We had done this, that operation M should be exhibiting distributive law. So this is showing distributive law. Exactly, you are just inverting everything into kit to brass space and presenting it as the same. Okay. Uh, yeah, of course the difference is here it was all uh, without any complex conjugate and all, but here everything is complex. It is transpose complex conjugate, which is dagger based. I'll leave that. Associative axiom. So this is very important. Uh, the fact that you got two vectors alpha and beta. Uh, so if you have a ket alpha matrix multiplied by bra alpha multiplied by uh, matrix M operator with ket beta, then this is like A, B, C. So A into B C equal to AB into C. That's the type of association. And but we don't change any of the positions. We just change the bracket position so that which one you multiply first and which one you multiply. So in a this is kind of a uh, left hand side right hand side inner product, because both will result in a, if you place the matrix and along with the alpha and beta, if you show up, example in this case beta is I minus I1 and alpha is 2I, both column matrix, and both are kit representation. And if you have a matrix of I 0 1, and then if you multiply, because this says first take A then do BC, this says first you say AB and then C. So if I represent by A into BC, so we have to take BC first. BC is nothing, M multiplied by matrix M multiplied by kit beta. So this is the multiplication, and this results in minus I minus 1 plus I and 1. So this is M beta. Now if we take a bra alpha, because alpha is this, so bra alpha will be rho matrix. So 2I, it will become 2 minus I, because you are flipping 90-degree anti-clockwise, or we got transpose and then taking the complex conjugate. So minus I plus this 2 plus 2I becomes 2 minus I. So rho vector, and this is the M beta. You take the M beta, then multiply, and then you 2 into minus I plus 2I. So it will become minus 2 plus 2I, and here minus I into 1, and so we see that this is equal to this is 2 minus I into minus I. So you have to multiply by minus I, and then we get a result of minus 2 plus I. Of course, we have to add this, multiply this plus this, and so overall we are getting minus 2 plus I. So this is what is it representing? It is representing that A into BC equal to B into C, and this what we can do is similar multiplication uh, we can do for uh, alpha bra alpha into M, and then multiply later by beta, and ultimately both of them turn out to be same. So this is the dual. So your ket alpha M, bra alpha M ket beta equal to complex conjugate of this thing. So beta will come this side. So beta M dagger alpha ket. So when you take the entire thing complex conjugate, your M, which is the matrix. So essentially this is like graphically shown. You have a row vector, you have a column vector, you have a matrix. So the operator, which is a matrix, can do A into B C equal to AB into C times, which is the the whole goal of this representation in terms of matrix was associative axiom. So associative applies here, and but it applies with some modification in the sense that at the end of the day you will find that M which is in the middle is sandwiched between the bra and a ket, which is showing that when you take alpha, beta, and beta alpha, they will be scalars at the end of it, and M will be a matrix which is the operator matrix. So dot products are maintained even if you have multiple vectors. The dot product is important, and that's what the associative law says, that you can manipulate like any other mathematical, exception that you have to do the complex conjugate and all those with respect to matrix as well as vectors. Hermitian matrix have real eigenvalues. So basically, if you have a vector which is Hermitian, we said what is a Hermitian matrix? If you have a adjacent self-adjoint of a matrix is same as the matrix, then you are going to have eigenvalues. So not every uh, vector has a eigenvalue. Only those which are Hermitian matrices, which is nothing but uh, taking a adjacent of a matrix, uh, and if the self-adjacent matrix is same, then they are called as Hermitian and they have eigenvalues. Now there are two interpretations which are important: bonds and Copenhagen. Bonds interpretation is for the two level, two for a one single qubit which is 2 to the power uh, 1, which is you have got 2, because qubits exist only if you have two linear combination. Minimum is 2, so it has a spin up and spin down, so it has 2. So there is no 2 to the power 0 equal to saying that it is 1. There is nothing like that. You have to have 2 to the power at least 1. And if you have 2 to the power 1, you've got 1 qubit. If you've got 2 to the power 2, then you've got 2 qubits, and accordingly, and so on. 2 to the power n. So, or we say that if you have n dimension, uh, n dimension comes in n minus 1. So, you say 0 to n minus 1. Okay. So, the bonds rule, before we go to Copenhagen interpretation, we should see what the bonds is there. Is there a bonds rule here? No. Okay. So, simply let me just state for two level, we represent psi ket psi as alpha uh, ket 0 plus beta ket 1. It's not written here, but that's what we represent as for two dimensions. And Bond's law applies to uh, two levels. That is two two basis state, which we say linear combination. Vector k psi being the linear combination of alpha ket 0 plus beta ket 1. And if we extend that to n minus 1 or n dimension, it was for two dimensions. So if we extend from two dimension to n dimension, then we are going to get the what you call representation of that as uh, a linear combination of coefficients which are going to be 0 to n minus 1. And so we say sigma 0, 0 to n minus 1 of the combination, that is the linear combination. In that case, we call it as A0, uh, A0, let's say ket 0, A1 ket 1, A2 ket 2, A2, A3 ket 3, and n minus 1 ket n minus 1. Basically, I am representing in this case 1, 2, 3, 4, 5 n minus 1. Even by decimal digit, you can represent. It doesn't have to be alpha, beta, and Greek letter. So it's abstraction, right? At the end of the day, we are just representing the abstraction. So that's the Copenhagen interpretation relates to the uh, the, the vectors. Basically, these are related to the vector space, and if the coefficients of those vector space are lambda, in this case we are saying that if n equal to 2, I will have lambda 0 and lambda 1, which will be the eigenvectors, eigenvalues corresponding to eigenvectors, and they are eigenvalues in the sigma z works space, which is what we are trying. And when we say we are interpretation, that means it's an observation. When you do any any operation means in quantum mechanics or quantum computer, operation always means you are taking a vector and transforming it to another vector by applying some operator, and the operator being matrix. So Copenhagen interpretation of Hermitian operator is simply that you are going to have a lambda I, which is it can be I can be 0 to n minus 1. So every coefficient lambda 0, lambda 1, lambda 2, lambda n minus 1, whatever that n happens to be. In this case, n equal to 2, which is nothing but the Bond's rule. So Bond's rule, if you say n equal to 2, it is lambda 0, lambda 1, then it boils down to ket 0, ket 1 with a sigma z as the matrix, Pauli's matrix, which operate on the two dimensions or two vector spaces, ket 0 and ket 1, and you are going to get a result of plus minus 1. Now, you can apply this to any vector ket I. That means ket I can be ket. When I say I mean I can take a decimal digit. I can say 0 ket 0, 1 ket 0, ket 1, 2 ket 2, 3 ket 3. So if I take a n equal to 4, then I am going to get 4 uh, coefficients. Those are lambda 0, lambda 1, lambda 2, lambda 3. They will be plus minus 1s respectively, and then corresponding to that, whatever uh, the summation I take, those summation will be for the respective ket 0, ket 1, ket 2, ket 3 with alpha with a0, a1, a2, a3 coefficient, and when we sum it, each of them will produce some results, and depending on how they are, if they are independent, then we'll have two independent qubits operating. If they are entangled, then maybe some may have some different interpretation. They may create some Bell states, what they are called, where you cannot really measure because they are not independent. So we'll not get into Bell states right now. We just say that at this time, if they are independent, then we are able to measure independently, and depending on the measurement or depending on the value, the direction and all that, like whether we are measuring the z basis axis, then everything is measured with respect to z, then all the interpretation has to be with respect to z axis, because that's the magnetic flux, the direction of magnetic flux that determines how the vectors are rotated based on the attraction towards the north or the south pole of the magnet, which is a measuring device for a for a what you call the subatomic spin of electron plus minus direction. So Copenhagen interpretation just extends the law for arbitrary quantum state and for arbitrary uh, finite states. I have to put a finite term there because it cannot be infinity, it has to be finite. So that 0 to n minus 1 shows the limit. You have 0 to, so for n dimension, it will be 0 to n minus 1. For m dimension, it will be 0 to n minus 1. So essentially, it is a finite state. Representation of a finite state observation on the vectors as they are rotated based on the um, operators being operated on them. And when we operate, if we measure, they will collapse to the respective state. And that is happening for any of the what do you call it, independent qubits. Now you can see here what I said. Maybe I should have pointed to here then. It's okay. So ket psi equal to a0, ket 0 plus ket 1 plus a n minus 1. That is into n minus 1. Now we can express this interpretation as a linear combination of eigenstates, also as projection operators we call pi. So instead of representing as m, sigma m, like alpha, ket alpha, m, ket beta, which is bra alpha, m, ket beta, we represented for uh, what you call the previous uh, eigenvalue, x eigenvalue representation. Same way we can represent here in terms of, like we saw here, this one, bracket notation, using bracket notation and matrices as we represented, row vector versus column vector with matrix sandwiched, which is here nothing but dot product. Same way in this case, we can do it using probability, and they call it as projection operator. So if you have get bra sigma and pi, which is the projection matrix or projection operator, then you can give this with the probability matrix. So projection matrix is nothing but that projects the state into subspaces. So pi is projection operator that will project an arbitrary vector into subspace spanned by ket I, and ket I we said. And in this case, what we are doing is this is shown not based on the what we did as an inner product, but this is showing projection operation is shown for outer product. So if you have a I, that is a ket I, which is a state space or a vector space of n dimension, then we are taking a outer product. So projection matrix, in this case, projection not matrix, but projection operator appearing as a matrix in the subspace is represented as pi equal to ket I bar, which is nothing but the outer product. So you got in matrix two products, one is the inner product, the outer product. Outer product is, inner product is scalar, outer product may be different. It is always a vector in the pointing to a, if you are going in two dimension, then the third dimension orthogonal is what? If you have xy, then we use generally right hand rule for a xyz as the pointing force being or the motion being pointing in the z direction. So this is somewhat different in the sense this is a vector. So outer space product is always a vector, and that even if it is a vector, how do you represent that? That is what you have to do tensor operation. So outer products are always tensor product of vectors. So most of the operations that happen in quantum mechanics are always representable as tensor product, because what you do in higher dimension is not as visible as we do in lower dimension, where we can really interpret it physically. There we have to, the abstraction is there, and that is why you will find that tensor operators are the most important, and they are represented as x with a circle on it, and you will see that, and how they appear as here I don't see, but it's a x with a circle around it. So you got a operation projection matrix, which is nothing but trying to get the projection. And when you do a projection of alpha and beta or beta and alpha, uh, they are what you call the complex conjugated, that factor appears there. Uh, so a inner product of alpha beta is equally uh, similar to beta alpha, which is complex conjugate, and that's what we do in the inner product. In our outer product, generally we use determinants to determine. So we'll get into that determinants and all, but this operation represents a matrix representation. If we are taking here, we have a ket 0. So the question is, what is ket 0? You have got one of the states which is out of the n state. Now there are n minus 1 states, 0 to n minus 1 vectors. All are column matrix representation. So this representation states that this ket 0, which has 1 at 0 level, it says lambda I 0, and same way lambda 1 being 1, lambda n minus 1 being 1. So there is only one of the values which is 1, rest of them are 0. And this is how the row vectors are, column vectors are represented for ket 0 to ket n minus. So if n is equal to 4, then you are going to get 4 states. That means there are 4 uh, basis states, and those are 0, 1, 2, 3. 0, 1, 2, 3. And those are represented as, if I want to say what is 2, for n equal to 4 and I equal to 2, you are going to get a pi, which is P2 in this case because I is 2. P2 is equal to ket 2 bra 2. Ket 2 bra 2 means it will come as, if you go and multiply, this is the row, this is the column matrix ket. So ket 2 is 0, 0, 1, 0, and bra 2 is just the rotation of it in the row basis. So it will be 0, 0, 1, 0. So you multiply this, you will find that entire space, you will get only one multiplication, and that is this into this, and that appears at the position here, which is in the part of the diagonal. So diagonal lambda I, lambda 0, lambda 1, lambda 2, lambda 3. So the lambdas always place themselves in the diagonal, and you get the, in this case it's 2, 2, so 0, 1, 2, 0, 1, 2. So this is the corresponding set. So that's the position where you are going to get a 1. That means unitary. This is unitary we are talking. So if it is coming to that, that means that's the only one, the ith diagonal, in this case 2, which is what, 0, 1, 2. That's the only one which is representing the projection matrix. So essentially the probability will come when you multiply this with the coefficients, right? So what we will see is that this is representative of a probability being unity at the point where we are looking for a specific vector. And if you take a square of that, 1 square is 1. So that's what you are going to get, ai square. And but if you go, because this is a linear combination, you are going to get a0, 0, a1, a0, a1, a2, a3, 4 of them, because there are 4 dimensions, a0, a1, a2, a0, a1, a2, a3. So, but you take the sum of 0 to n of n minus 1, that is 0 to 4, 0 to 3 in this case, because 4, n minus 1 is 3. So a0 square plus a1, a0 square ket 0 plus a0, a1 square ket 1 plus a2 square ket 2 plus a3 square ket 3. And if you take that as the uh, previously we had seen that Copenhagen interpretation. So if you take this interpretation, the probability is nothing but sum of the ai square. So basically we have to take all ai and square of them. Ultimately it is all boiling down to that only one of them is 1. So only that particular one will be measured if you go by projection matrix. So that's the same interpretation. It's no different, but you can take a summation, and because until it collapses, you got all values possible. So, but once it is collapsing, then it collapses to a particular state, and that in this case we said it is, our assumption is we are going to get under 2. Therefore, the probability of that is a certainty in the sense that until it collapses, it is uncertain. Once it collapses, it is certain that we are going to get that element. And that is the state. And eigenvectors are those, eigenvalues are this, and eigenvectors are this. So these are our eigenvectors, our eigenstates, and these are the eigenvalues which comes across the diagram. And they are obviously one of them is 1, depending on which state it collapses to. And if you take a sum of this, and that gives you that is the trace, we call it. So we will be tracing it to this particular place to be able to get the value. Okay, and that's all. And here what we have, some of the assignments. Please refer to them. And I think we had done this previously, and this is assignment 01, I believe. So this is what you are doing. Sigma y square is equal to I. I think we had our classes in date, but anyway, let me just recollect. Sigma y square is I. That is you have to do it with the hand. Take the value of sigma y. Sigma y, you remember, for Paulus matrix is y. Y means it will come to 0, I minus I 1, and then you can see that, verify that, because you will always tend to. Um, so you can see here, not this one, but yeah. So here it is 0 minus I 0. So y, since we are talking about y 0 minus I 0, I go by rho, so it has to be 0 minus I 0. So if you go to 0 I 0, 0 minus I 0, that's what the expectation is, that this calculation will be able to do with multiply the same vector twice to get a square of it, and you end up in identity. So you can use collab to do this, or you can do numpy with the array row basis, as we said always in the pi. You can use 0 minus 1 can compute this and print the sigma y using the numpy line. Same way, polymetrics for sigma z are asked to prove or calculate using collab. And Hermitian, it is nothing but uh, we take the adjacent or adjoint of a matrix. So self-adjoint are nothing if the self-adjoint is, if the complex conjugate transpose of matrix A is equal to A, then in this case A is nothing but sigma y we are taking. So for the sigma y, if we take complex conjugate transpose, and if it turns out to be same, that verifies that it's a Hermitian matrix. And the fourth one, operator on uh, polymetrics on bra and kit. So in this case, we are taking a sigma y kit 0 and bra 0 kit y as a sample. Verify using collab. This you can use the collab, the Python with the libraries and all, so that you are able to do the 0 spin and then print the 0 spin shape and represent that using the dot. So this is some uh, library you can use directly and show. I think that's all I have for the day, for the session. I will only say that the second, we'll discuss this in the office hours today when we have the, but references are there, and here the references for the book, as well as this understanding three blue, brown, one brown. Linear algebra is important. Before we go on to the next session, we will have to make sure that we have everything covered. Your Wednesday evening link is here. Today 8:30 p.m. PDT, Pacific Daylight Time. Today is the longest day. We are going to have fun. Hopefully, we'll meet today and then go over the second session, session 4, part 2 problems. Then, and with that, I will close the meeting, and the question and answer will have at an appropriate time today evening. And if there is anything, this session might be replaced by Google if since I interpreted what he had done, and hopefully he'll be able to record it. In that case, we'll replace that record with this record. Thank you.